This is the first example that we will see involving a titration situation. So we are told an IV line was ordered to titrate between 2 and 3 micrograms per kilogram per minute. We are to increase the dose by 0.1 micrograms per kilogram per minute until the patient's systolic blood pressure stabilizes below 120 millimeters of mercury. We're also given some information about the patient, weighs 90 pounds, and the IV solution that we will be using. The first thing that we want to do is to find the initial rate to set the IV pump. And we're going to put all this information in the chart. So before we jump into this, just to recall, we know with titration, as we had read and we watched some videos, a patient's going to be ordered to receive a beginning amount. And in this problem, we're actually not told to start at anything in particular. So what that means is we're going to assume we start at the minimum dose of 2 micrograms per kilogram per minute. And depending on whether or not the patient is responding the way we think he or she should, we're going to adjust the medication. So in this problem, the patient needs to, and we're looking for, their blood pressure to stabilize below a particular amount, the systolic blood pressure, that is. So if the blood pressure does not stabilize after this initial dose, what we need to do is to continually increase that dose by 0.1 micrograms per kilogram per minute. So what this requires us to do is to make multiple calculations. We're going to start with an initial dose, which, very much like a critical care situation, will require an initial milliliter per hour rate. But then whether or not the patient responds positively, that's going to dictate if we need to increase the dose. And if it does increase the dose, we might have to continually calculate a new rate because the dose is going to increase. So what I'm going to do, and that's why we have a chart here. We have a chart here so we can organize all this information. I'm going to go ahead and fill out the first line. The time, I just made this up, it's 0900. The dose, the initial dose that the patient is set to receive, we are not told start at such and such, which means we should assume we'll start at the minimum value. The minimum dose that a patient would receive would be 2 micrograms per kilogram per minute. And what we need to do is to figure out what rate in milliliters per hour should we set the pump to. So this is very much like a critical care situation that we saw in some previous videos in this modules. So what I'm going to do is I'm going to convert micrograms per kilogram per minute into milliliters per hour. In order to do that, as we saw with critical care, I need to multiply by the patient's weight. So I'll start by writing my dose, 2 micrograms per kilogram per minute, and I need to multiply by the patient's weight in kilograms. And if I do that, then I'll know the total number of micrograms per minute. Up above, I'm told the patient weighs 90 pounds. So I'm going to bring that to the side, and I know 90 pounds. I'm going to divide by 2.2 because there are 2.2 pounds in 1 kilogram. And I know with weights, especially weights over 10 kilograms, I'm going to round to the tenths place. So if I take 90, I divide by 2.2, I get approximately, rounded to the tenths place, 40.9. 40.9 kilograms. So that's the patient's weight in kilograms. Now I'm going to, as soon as we multiply by that factor there, kilograms will cancel. I want to convert micrograms into milligrams because I need to use the dosage strength of the bag, and the bag is 80 milligrams for 200 milliliters. So in order to get to milliliters, I'll first convert my micrograms into milligrams. All of this is a bit of a review, so if you think I'm going a little too fast, you might need to go back and review some of the videos that we saw maybe with the critical care and the dosage by weight. So by multiplying by 1 over 1,000, that'll convert into milligrams. Finally, milligrams into milliliters. All of this is a review of the critical care problems that we saw. So I circled milligrams, but I shouldn't have, because milligrams is going to be going to milliliters. That's what I want. And now finally, we'll go 60 minutes into 1 hour. Minutes will cancel, be converted into hours. So what I'm going to do is multiply all of the numerators, very much like I did in the critical care example. So 2 times 40.9 times 200 times 60 gives me 981,600. And if I multiply all of the denominators, 1 times 1,000 times 80 times 1 gives me 80,000. Now when I put that quotient into my calculator, I will get exactly 12.27. I need this exact value, right? That's the exact value. It's going to be very important that I get the exact value. But knowing that information, that's great. That's the exact value of this division problem. But what am I going to set the pump for? The pump needs to be set to the 10th place. So to set the pump, I will set the pump to 12.3 milliliters per hour. Now, let's just think back what we did. We were told the minimum dose was 2 micrograms per kilogram per minute. I did the work to convert that to milliliters per hour. In order to start this titration dose, I would start the pump for 12.3 milliliters per hour. In the next few examples, what's going to happen is we're going to need to adjust this rate because, as we'll see, the patient is not going to respond positively to this. So we're still not stabilized, so what we need to do is to adjust. So let's look at the next slide. So now we need to recall the order we just completed. We're titrating between 2 and 3 micrograms per kilogram per minute, and we're to increase the dose by 0.1 micrograms per kilogram per minute until the patient stabilizes. We are told here we are to assume that the patient's systolic blood pressure did not stabilize after that initial dose. So what we need to do is to make an adjustment. What is that adjustment? Well, according to this problem, we need to increase the dose by 0.1 micrograms per kilogram per minute. So if I were to add 0.1 micrograms per kilogram per minute, I would have 2.1 micrograms per kilogram per minute. So that's great. The dose increased by 0.1 micrograms per kilogram per minute. Now what I need to do is to go and reset the pump. So what's that going to mean? That means I need to redo my dimensional analysis. So what I'm going to do is pause the video and I'm going to redo the dimensional analysis, but not with 2 micrograms per kilogram per minute, but with 2.1. So I went ahead and started with my dose of 2.1 micrograms per kilogram per minute, and I followed the same steps. I multiplied by the patient's weight, I converted micrograms into milligrams, then used the strength of the bag to go into milliliters, and finally converted minutes into hours. I multiplied all the numerators and denominators to find that the patient needs to or should be receiving 12.8835, and I'm writing the exact value of what I got when I did that division problem, and you really should get in the habit of doing that. Let's write the exact value and now round, right? What are we going to set the pump for? I'm going to set the pump for 12.9 milliliters per hour. And the reason I'm doing 12.9 is because we're going to the 10th place. Most pumps are going to be precise to the nearest tenth of a milliliter. So, what did we see right then in this problem? We had to come back and see that the patient did not stabilize, and a half hour later, from 0900 to 0930, the patient needed to be given an increase of the dose. So we had to redo all of that calculation that we saw previously. We're multiplying by the weight, going into the different metric units, and using the bag. We did that exact same thing to figure out what the rate is. So let's look at the next slide. So now we're told that we're supposed to assume that the patient's systolic blood pressure still did not stabilize after the initial dose. So we need to make the appropriate adjustment and determine the new rate to set the pump. Okay, this is getting a little bit of annoying, right? We're doing the same calculations over and over again. Of course, we want the patient to stabilize. That's the goal of the situation. But with titration, we aren't always guaranteed that that's going to happen. So what we need to do is to continually adjust the dose. So what I'm going to do right now is to once again adjust the dose by adding another 0.1 micrograms per kilogram per minute. I'm going to add 0.1 to get 2.2 micrograms per kilogram per minute. So I'm not going to spend too much time on this. You should know what to do. Go ahead and pause I'm going to pause the video. If you want to pause it and try it, I'm going to do all the dimensional analysis once again to get milliliters per hour. So I went ahead, did the same calculation that we did on the previous 2 pages there, and I got 13.497 as my exact value, and then I rounded that to the tenths place to get 13.5. Now, as you might be able to tell, this could get a little bit tedious if we have to do this calculation over and over again. Thankfully, there is a better way, and we can summarize all this information by considering the relationship between the dose and the rate. So let's go to the next slide and summarize this relationship. And so on this page we see we can take and organize this information in a little bit of a nicer table. So we have the dose. We saw when the dose was 2 micrograms per kilogram per minute. The exact rate was 12.27 milliliters per hour. We know it was 12.3 when we set the pump, but this was the exact rate. We also see the increases, the adjustments to 2.1 and 2.2, and the rates associated with those. Again, the exact values in milliliters per hour. Now, what we want to be able to do is to see if there's a relationship between the dose and the rate. And what I'm going to do is to take the dose and I'm going to divide it by the rate that it has, or what it's associated with. And that's going to give me this value of K, which I'll call my constant of variation. And I just want to see what happens when I set a ratio up of the dose and the rate. So if you take 2 for 2 micrograms per kilogram per minute, and you divide that by the rate associated with that dose, which was 2.27 mLs per hour, what does that simplify to? And so if we get our calculator out and we take 2 and divide it by 12.27, we get that this is approximately 0.16299. So I'm just going to write that out a little bit. And that continues. Now, if you take the dose, the new dose, the adjusted dose of 2.1, and again, that's micrograms per kilogram per minute, and divide that by the rate that it's associated with, which is 8835, let's see what we get. And again, this is milliliters per hour. 2.1 divided by 12.8835. And we get exactly the same thing. And I'm going to guess if I do the final combination of 2.2 and 13.497, I'm not going to put in the units in this case. I'm just going to put in the numerical values. Let's see what happens. Yep, we get exactly the same thing. And so what we're finding is that the dose and the rate have a direct variation. That's one way to describe this. The dose and the rate have what's called a direct variation. And that's just a fancy way of saying there is a proportional relationship. There is a proportional relationship between the dose and the rate. And we have seen that proportional relationship. And what I'm going to do down below is kind of summarize this. How might we be able to use this fact? If we know the dose and the rate always simplify to the same value, which we call K, they always simplify to this value, then we can use this proportional relationship to do and calculate adjustments. And what I mean by that is if you know that the dose, which could be in micrograms per kilogram per minute, or it could be in another dose. It could be micrograms per minute, or it could be milligrams per minute. But you know the dose, and I'm going to put 1 for the first dose. The dose and the rate, that ratio will always be equal to and constant. So it will always be equal to the dose and the rate for some other adjustment. So if you increase the dose, then you know that the rate needs to increase by that same multiplicative factor. If the rate has changed by some multiplicative factor, then the dose has to as well. So again, we can use our understanding of proportional relationships to consider the multiplicative and the division properties between all of these values to help us, and we could always do cross multiplication as well, but we can use a proportional relationship to solve for the adjustments. And that means we don't have to do dimensional analysis over and over and over again, because we have and know that the relationship between these ratios will always be constant. So let's use this fact to address this next question. Suppose the patient has still not stabilized. We're not going to use the equation. I guess it is an equation, but we want to use the proportional relationship, is what that should say. Use the proportional relationship between the dose and the rate to find the new rate to set the pump. And so again, what I know is that the dose and the rate are always going to be simplifying to the same value. So dose 1 and rate 1 will always equal dose 2 and rate 2. And to be clear, this is just one way to write this. There's actually other ways to set this proportional relationship up. But if you know that the minimum in this case was 2 micrograms per kilogram per minute over 12.27 mLs per hour, that was the ratio. If we set it up using the first dose and the first rate, we know that that's going to have to be equal to an equivalent relationship of micrograms per kilogram per minute and milliliter per hour. In particular, what I'm looking for is the rate. I don't know this rate, but I do know the new adjustment is, it went from 2.2 was the previous. If we were to increase that to the new adjustment, it would be 2.3. So I now have this proportion to solve. So I'm going to cross multiply, and I'm going to use x as my variable. And if I cross multiply, I get 2x equal to 12.27 times 2.3. And I'm not going to put in the units when I'm running that equation. I don't want to complicate matters. I used the units in the proportion to help me align and keep track of where my unknown value was. But if we set this up and now we divide both sides by 2, you get 12.27 times 2.3, and divide that by 2, you get an exact value of 14.1105, which means if we round the pump, and we are setting an IV pump, this would be 14.1 ml per hour. So if we were to do the dimensional analysis again, this is what we would see. But we can avoid doing all of those same multiplicative and conversion factors by just setting up a proportion.